In this lesson, we're going to talk about a new operation that exists between two vectors, and it's called the dot product. And it doesn't have, unlike scalar multiplication or vector addition or subtraction, there's really no other previous operation that you've learned with scalars. I guess you could kind of say it's maybe how you multiply two vectors together. Let's take a look at the definition of the dot product. So the dot product between two vectors u and v, u dotted with v, and we do use the dot, okay, for this symbol, is equal to the magnitude of u, times the magnitude of v times the cosine of theta. Of course, theta is the angle between the two vectors when they're placed tail to tail. So you can imagine that and that. You've got your angle theta, and there's your definition of the dot product. Now, this is sort of a geometric definition, because when we talk about the two vectors, their magnitudes, and especially the angle between them, it's sort of implied that we must have a picture of them. Because if we had these vectors in algebraic form, we wouldn't know the angle between them. Okay, not without quite a bit of trigonometry work. So this definition is for geometric vectors, and we'll get into the algebraic vectors soon. Okay, dot product is also sometimes called the scalar product or an inner product. You can see why it's called scalar product. So u dotted with v, the magnitude of u is a scalar, the magnitude of v is a scalar, and the cosine of theta is a real number as well, so that's also a scalar. So this is in fact going to give you a scalar. So the dot product takes two vectors, it operates on two vectors, but it returns a scalar value. So we could use the definition to come up with a couple examples here. We don't really need a picture of this, but we could certainly create one. So here u dot v is equal to the magnitude of u, which is 7, times the magnitude of v, which is 15, times the cosine of 60 degrees. Okay, of course, cosine of 60 is a half, so this is really just 7 times 15. Oops. 15 times a half, which gives 52.5. Okay, and I'll do one more example just to show you one other thing. In this case, in part B here, example B, u dotted with v would be equal to 13 times 55 times the cosine of 150 degrees. Now the cosine of 100, so 13 times 55 is 715, but the cosine of 150 degrees is negative root 3 over 2. Okay, that's the negative of cos 30 degrees. Sorry about that. So I just want to point out that the cosine can in fact be, or sorry, the dot product can be a negative number. In this case, if we end up rounding it, we get about negative 619.2. So if the angle is obtuse, the cosine is negative just from the cast rule. So that means that it's possible that your dot product could also be a negative number. So what does the dot product actually represent? Like, why do we have this definition? There's a few reasons. It's sometimes seen as what's called an angular relationship. And I'll talk about what I mean by that. So imagine you have two vectors, u and v. And of course you have the angle between them. Okay, so you've got u and you've got v. And you're multiplying the magnitude of u times the magnitude of v. However, so it's kind of like, it's kind of like multiplication. You could imagine that to multiply or to dot two vectors, you want to multiply their magnitudes together, but we don't quite do that. We also include the cosine of the angle between them. So I would look at it like this. If you were to imagine drawing this little line right here. Okay, so look at this right angle triangle I have here. The cosine, if I look at this side right here, okay, and I'll actually just draw it right there. Okay, the cosine of theta is this length divided by the magnitude of v, okay, adjacent over hypotenuse, which means that this length right here that I've drawn in with the red dash is actually the magnitude of v times the cosine of theta. So in a way, what I'm calculating is the magnitude of u times the magnitude of v, but only the part of v that's going in the same direction as u. So it's like I'm multiplying the two vectors' magnitudes together, but only the portion of the magnitude of one vector that operates in the same location as the other. Okay, that's kind of how you can think about it. And then, of course, if I keep moving this angle, okay, so if I move it so it's greater than 90 degrees now, well, now this shifts over here, and now, oops, sorry, and now I get a negative answer, which kind of makes sense because the portion of v, there's no portion of v that's operating in the same direction as u. It's going in the opposite direction instead. So sure enough, I get a negative number. So that's kind of one way you can think about it. I don't know if that made any sense or not. It doesn't. If it didn't make sense, you don't really need to worry too much about it. It's just a way of visualizing it. You could say the dot product's similar to multiplication. It's like multiplying two vectors together, but like I said, multiply their magnitudes, but then only the portion of the one magnitude that sort of operates in the same direction. We're going to learn a lot about the properties of the dot product, both in this lesson and the next one, and some of those properties are very useful. And one other thing is that when we learn the definition for how you do the dot product between algebraic vectors, we're going to find that this connection is actually incredibly useful. So the definition for how you dot two algebraic vectors together is very simple, yet the fact that it's equivalent to this definition right here is very useful. We'll get to that in just a second, you'll see what I mean. Before we do that, though, let's take a look at this idea here. Prove that two non-zero vectors, u and v, are perpendicular if and only if u dotted with v is equal to 0. A couple things about this proof. This is an if and only if proof, meaning that the statement goes both ways. Given that u and v are perpendicular, it means their dot product is 0. The other way around also must be true. If the dot product is 0, then u and v must be perpendicular. Technically, we should prove this both ways. So I'm going to start with what's called the if part of it. So if u dotted with v is equal to 0, we then need to prove that u and v must be perpendicular vectors, okay, intersect at 90 degrees, or the angle between them is 90 degrees. So if u dot of v equals to 0, that means that the magnitude of u times the magnitude of v times the cosine of theta is equal to 0. Well, notice that these are two non-zero vectors, meaning neither u nor v is equal to 0. So it must be that the cosine of theta is equal to 0. Well, when does that happen between two vectors? Must be that theta is 90 degrees. Okay, it could be 270, but of course the angle between two vectors is never 270. It would just be the 90-degree angle, and therefore u and v are perpendicular. The other part, so this is sometimes called, this is the if part, is the only if part. So the only if part says that u is perpendicular to v, and we must now prove that the dot product is equal to 0. Okay, so if u is perpendicular to v, then theta must be equal to 90 degrees. Since they're perpendicular, and u dotted with v, which is equal to the magnitude of u times the magnitude of v times the cosine of 90 degrees. Of course, the cosine of 90 degrees is 0, which gives us u dotted with v is equal to 0. And we've done the second part of the proof. So if and only if statements are very, very strong statements because they basically mean that the idea of vectors being perpendicular and the idea of their dot product being 0 are completely equivalent statements, meaning that we can replace the word perpendicular vectors with vectors whose dot product is equal to 0. And actually, anytime in this course going forward working with vectors, if you hear that vectors are perpendicular, you should immediately think that their dot product is equal to 0. It's going to be a very helpful strategy to have. Let's think about what happens if you take a vector and you dot it with itself. So let's say we got vector x and we want to dot it with vector x. Okay, well, it's the magnitude of x times the magnitude of x times the cosine of the angle between x. Well, x is the same vector. So if we have one vector on top of another vector, okay, or the two vectors, the angle between them, theta, must be equal to 0 degrees. So we get the magnitude of x times the magnitude of x times the cosine of 0. Well, the cosine of 0 is equal to 1, and so we just get the magnitude of x squared. So there's a property of the dot product that's very similar to multiplication. If you dot a vector with itself, you're going to get 0. Pardon me, you dot a vector with itself, you're going to get the magnitude of the vector squared. Kind of like when you multiply two numbers, a number by itself, you get that number squared. Suppose we're working with algebraic vectors and we want to dot those vectors together. Finding the angle between two vectors when they're in component form is very difficult. However, the dot product, we have a definition for the dot product. If you have two vectors in component form, two algebraic vectors, you can get the dot product just by multiplying the corresponding components together and adding. That's a very simple operation. You can clearly see too that, since A1 and A2 and B1 and B2 and so on are all real numbers, that you're going to get a real number when you do this. So looking at a simple example here, how do I calculate the dot product between these two vectors? I just follow this definition right here. So A dotted with B is going to be equal to 1 times -2 plus -3 times 0 plus 5 times -4. Something that's simple enough you can almost do it in your head. And let's try it here. Let's see, -2 plus 0 plus I get -22. Okay, something that's very important, I can't stress enough, is the fact that this definition right here, this is for algebraic vectors, that this definition is equivalent to this definition right here. They're exactly the same, okay? Any vector can be, it's not like there's a group of vectors that are geometric and a group of vectors that are algebraic. Every geometric vector has an algebraic vector that's the same vector, and every algebraic vector has a geometric vector that's the same vector. The dot product is equivalent. So doing this with two vectors is actually the exact same thing as doing this. So if I were to, for example, take U and V and calculate their magnitudes, okay, and then somehow calculate the angle between the two vectors, you can imagine them being drawn on the coordinate axis. If I were to calculate their magnitudes and calculate the angle between them, I could apply this formula right here, and I would get the exact same result as using this formula right here. Okay, I'm going to show why that's true at the end of the lesson. We'll do the proof for why they're the exact same. But what that means is there's the connection between those two are very helpful because this is relatively easy to do. So if I look at -22, I can tell one thing about vector A and B. What do you know right away about vector A and B? Since their dot product is negative, it must be that the angle between them is obtuse, okay? From this idea that we talked about down here, okay? And we saw the example right here. If the cosine of an obtuse angle is always negative. So we know the angle between these two vectors has to be obtuse. But we can go further. We can actually calculate the angle between two algebraic vectors through the dot product, because the dot product is relatively simple to do. X dotted with Y is equal to 2 times 0 plus 3 times -1 plus -4 times +1. In this case, our dot product is, let's see, -3, -7. So again, X and Y are also going to be two vectors whose angle is greater than 90 degrees. We can figure out exactly what it is, because we also know that X dotted with Y is equal to the magnitude of X times the magnitude of Y times the cosine of the angle between them. Or we can rearrange that to say that the angle between two vectors is really their dot product. Sorry, is really, yeah, their dot product divided by each of their magnitudes. Now in this particular example, we've already figured out the dot product. We just need the magnitude of both of those vectors. Sorry, I didn't leave myself a lot of room here, but I'll figure the magnitudes out in the top corner here. So the magnitude of x is equal to the square root of 2 squared plus 3 squared plus negative 4 squared, or root 29. And if you do the exact same thing with the magnitude of y, you should get the square root of 1 squared plus 1 squared is just root 2. So then I can fill everything in there. I've got negative 7 divided by root 29 times root 2. Okay, using a calculator, inverse cosine will give me that angle. We can just round it to the nearest degree, and you get about 157 degrees. So there you go. There's how you can, this is now, I mean, this is a pretty key example. Anytime I want the anytime I want the angle between two vectors, I can use the dot product, this formula right here, to calculate that. So now imagine having vectors in 3 space. We can now calculate the angle between those two algebraic vectors in 3 space. And that is actually useful in analytical geometry of 3-dimensional figures, okay? You can find point-to-point vectors. You can find the angle between those vectors. Allows you to calculate the angle between, say, diagonals of cubes and things like that. And some of the homework questions are going to ask you to do that. Okay, this next problem asks you to show that two vectors are perpendicular. Well, if they're perpendicular, it must be that their dot product is equal to 0. So let's look at A dotted with B, okay, or 15, 0, negative 3, dotted with negative 1, 5, 5, which is, of course, 15 times negative 1 plus, well, 0 plus negative 3 times 5. Oh, I made a mistake here. Let's see, 15. No, I made a mistake in the problem. Sorry, this is negative 30. This is a flawed question. They are not perpendicular. If they were perpendicular, their dot product would be equal to 0. And I guess I've messed this question up. If I could redo this, but there's no point. I think it's a pretty simple idea. So sorry about that. Show that they are not perpendicular because they're not. Now we enter the last part of this lesson. So let x, y, and y be vectors in 3 space, such that x is x1, x2, x3, and y is y1, y1, y2, y3. Why is it that x dotted with y is either equal to the magnitude of x times the magnitude of y times the cosine of theta, so there's the geometric definition, and it's equal to x1, y1, x2, y2 plus x3, y3. So you're basically saying in this example, why is it that the algebraic and the geometric definitions are exactly the same? Why is it that this simple idea of multiplying and adding components is the same as calculating the magnitude of each vector and multiplying those by the cosine of the angle between them? This proof's a little bit long, and it's tricky to start. You would have a hard time knowing how you start this proof. I'm going to walk you through it so that you've seen it at least. I've done all the work ahead of time because it's quite a bit of writing if you've already looked at it. Okay, so to start with, I got my picture of x and y, of course, and the angle between them. I'm going to use the idea that we know how to calculate the magnitude of x plus y. Okay, so based on our definition of x plus y, remember that you can complete the parallelogram, okay, like this. Of course, this angle here is 180 minus theta. This is y again over here. Okay, and we use the cosine law to calculate the length of the diagonal. So adding using the parallelogram law. Next, we also know that the cosine of 180 minus theta is equal to the negative of cos theta. Okay, so that's just using the cast rule. If this is cosine, if this is theta here, okay, cosine is equal to x over r, okay, just using the cast rule. But we also know that that is the opposite of what we get over here, okay? Because this is now negative x. Okay, so I can replace cosine of 180 minus theta with negative cos theta. Okay, we've seen this before. That makes this negative into a positive. And here we go. Okay, nothing new yet. We did this on our first lesson on vector addition. Okay, that's how you can calculate the sum of two vectors geometrically. So I'm going to flip back and forth between talking about x and y, talking about them in component form, and talking about them in geometric form, okay, like the picture of the vectors. Here I'm talking geometric. I put a little star beside this equation because we're going to, sometimes when you're doing a proof and you want to refer back to an equation, you might just use a simple little star. Okay, let's look at the left side of this equation right here. And now notice what I've done is I've taken these vectors, sorry if that's a bit messy, but I've said, okay, x plus y squared is I'm going to now express them in their component form. So x is x1, x2, x3, and y is y1, y2, y3. So I'm looking for the magnitude of these two vectors added, sorry, the sum of these two vectors squared. Okay, well, this vector right here is really this vector right here. x1 plus y1, x2 plus y2, x3 plus y. This is a vector. Okay, and I'm looking for its magnitude and squaring it. Okay, well, here's how. This is now like a vector with three components. This is how you calculate its magnitude. The square root, okay, you sum the squares and take the square root. Okay, notice next that the square root here and the squared, so the squared right here, and the square root, because I'm figuring out the magnitude of a vector algebraically, they cancel out. And so I just get this right here. This is what x plus y squared looks like. The magnitude of x plus y squared looks like. I'm going to expand that. And there we go. Okay, you multiply that out using FOIL. x1 squared plus 2x1 y1 plus y1 squared. So I'm taking x1 plus y1, multiplying it by x1 plus y1, and I get this right here. These are just numbers now, right? Okay, x1 is a number, y1 is a number. Do the same thing with this one. I get this right here. Do the same thing with the last one. I get this right here. Okay, each of these has 3 terms, so I've got 9 terms altogether. Next, I'm going to look at the right side of that equation that I showed you. Okay, so the right side of the equation, star again, just so remember, was this right here. Okay, adding vectors again. Now, line by line. The magnitude of x, again, is the square root of x1 squared, x2 squared, plus x3 squared, and then all squared. Same with this. So I just replace these. This is how you find a vector's magnitude. Notice that I didn't do that with here and here. Okay, I left those alone. You're going to see why in a minute. Okay, the square root and the square root cancel out. Okay, so I just get this right here. And now I'm actually done with the right side of this equation. So basically, I took my start equation. Okay, I took that's just this right here. I took the left side of it, which is this, replaced it with its components, or algebraic vector, and I got this messy equation right here. I then took the right side of the equation, and I replaced the components here and here, but I left this alone. So now I've rearranged the right side and the left side. Well, they're still equal to each other. So I recombine them. Okay, I just basically broke up the left and the right side of that equation because they're so long that if I did it all at once, it would just be a lot of writing. So now I know that this big messy equation is true. But look at this. There's all sorts of stuff that cancels out. For example, notice that there's the left side of the equation on the top and the right side on the bottom. They don't even fit on a single line, but those will cancel out. Subtract that off both sides. Same with this. This cancels out and this cancels out. This cancels out and this cancels out. There's others. Oh, I missed this one and this one cancel out. Same with the y2 squareds. They're going to cancel out. And the y3 squareds are going to cancel out. So now I'm just left with this whole line right here, and this, and this, which looks exactly like that. So it must be that this is true. Divide everything by 2, and look what you get. There you go. There's the proof. Okay? The magnitude of x times the magnitude of y times the cosine of theta is equal to x1, y1 plus x2, y2 plus x3, y3. So this relationship is true, and then we call this relationship the dot product. We call this the dot product and this the dot product. And so there you have it. I know that that's a really messy equation. I would never expect you to get that on your own. it's getting started on this proof that's difficult. Okay, that's it for this lesson. Thanks.